Welcome back, scholars. In today's video, we're going to continue looking at factoring strategies that can be used to find the roots or zeros of a polynomial. Let's get started. Back when we were solving quadratic equations, we looked at a factoring strategy called U-substitution. We're going to bring back that strategy here with these higher degree polynomials and use it in exactly the same way. For example 1 on the left, I have x to the fourth minus 4x squared plus 3 equals 0. I'm going to start by using my exponent properties to rewrite this first term, x to the fourth, as x squared quantity squared. Then I'm going to show in blue that we have an x squared in the second term as well. I'm going to use that placeholder u here to represent x squared. Now let's rewrite our equation showing that u substitution. We have u squared minus 4u plus 3 equals 0. That's a simple quadratic trinomial on the left, and we'll go ahead and factor that by looking for a pair of factors whose product is 3 and whose sum is negative 4. That will be negative 3 and negative 1, and I'll write that left-hand expression in factored form like this. Now we're ready to solve for our zeros. Let's go ahead and resubstitute x squared for u and then solve for our values of x as usual. We'll have x equals positive or negative square root of 3 on the left-hand factor, and we'll have x equals positive or negative 1 from the right-hand factor. That's 4 roots in all for a fourth degree polynomial. Now, before I move on past this example, I want to point out that strictly speaking, you did not have to use substitution here. In fact, if you look at this last line of work, where we replace the u with x squared, notice that we could have used our trinomial factoring pattern here to look for two numbers whose product is 3 and whose sum is negative 4. But instead of that first term being x, it will instead be x squared in order to generate that leading coefficient of x to the fourth. Let's look at example 2 on the right now. This time, I notice that my trinomial has a greatest common factor or a GCF, so I'll go ahead and factor out that x. This leaves behind an x to the fourth minus 26x squared plus 48. Once again, at this point, we could just use our trinomial factoring pattern if this expression factors easily, which it does. But let's just show how substitution could work here as well. Again, I'm going to rewrite my x to the fourth as x squared quantity squared using my properties of exponents. Then I'll let u equals x squared and substitute u for both x squareds in my expression. This leaves the quadratic trinomial u squared minus 26u plus 48. We'll think of two factors whose product is 48 and whose sum is negative 26. So this will have to be negative 24 and negative 2. Go ahead and replace u with its actual value, which is x squared, and from here, you'll set each factor equal to 0 using that zero product property and solve for your values of x. Since this is a fifth degree polynomial, we expect to find 5 roots, and that's exactly what we have. 0, positive and negative 2 times the square root of 6, and positive and negative square root of 2. At this point, we've looked at several general strategies for factoring, but we haven't explicitly talked about some of the common factor patterns that arise with these higher degree polynomials. When we looked at quadratics, complex numbers, and radical expressions, we frequently saw this difference of squares pattern. Altogether, these patterns are part of a group called polynomial identities. You will see these patterns consistently throughout this course, pre-calculus, calculus, and beyond. So it's extremely important that you're able to recognize them not only when written from left to right, but also when written from right to left. For our remaining examples, we're going to practice using the sum and difference of cubes. Notice that the left-hand side shows the product or standard form, also known as expanded form, and the right-hand side shows the factored form, which consists of two factors, a binomial and a trinomial. For these remaining 3 examples, we are just factoring, not solving. I want you to be very intentional about reading the instructions and distinguishing between the two. Factoring means rewriting an expression in an equivalent form. Solving, on the other hand, requires that you have an equation, meaning a comparison between a left-hand and a right-hand expression, and you're finding a specific value or values for x that make that equation true. As you can see, these are all expressions, not equations, so there's nothing to solve here. All we can do is rewrite these in an alternative form. So we'll do exactly that, and we're going to write each of these in factored form. Let's start on the left, where we have x cubed plus 27. That's a sum of 2 perfect cubes. So what you're meant to see here is that a cubed plus b cubed pattern. This case, the a term is x cubed and the b term is 3 cubed, which is another way of writing 27. Using that sum of cubes identity, we have a factored form of x plus 3 times x squared minus 3x plus 9. Underneath the factors in yellow, I've noted the position of a and b in the binomial and trinomial so that you can connect this back to that factoring pattern. In the middle, example 4, we have x cubed minus 125. This time we have a difference of 2 cubes, so you are meant to see this a cubed minus b cubed pattern. In this case, the a term is x cubed and the b term is 5 cubed, which is another way of writing 125. In factored form, following that factoring pattern, I have x minus 5 times x squared plus 5x plus 125. Once again, I've noted in yellow the a and b values in their respective places so that you can connect this factored form back to that pattern in your notebook. Last example, number 5, I have another difference of 2 cubes. This time we'll have to exercise our detective skills. This 8x cubed can be rewritten as 2x quantity cubed, and the 343 can be written as 7 cubed. Again, like the previous example, you're meant to see that a cubed minus b cubed pattern, which will be 2x quantity cubed minus 7 cubed this time. In factored form, we'll have 2x minus 7 times 4x squared plus 14x plus 49. Pay very close attention here to that a squared term in the trinomial. It's 4x squared because we are squaring the entire quantity a. That's 2x quantity squared, which is 4x squared, not 2x squared. Now, one last thing I want to talk about concerning these factored forms. Let's say that you're using this technique to solve a polynomial equation. In other words, let's go ahead and set each of these factored forms equal to 0 and say that we are now solving a polynomial equation. You can use the zero product property with the binomial to find one of your roots. For example, x equals negative 3, x equals 5, or x equals 7 halves. But these trinomials, despite their appearance, are not factorable. So your only other option then is to either use the quadratic formula to find the zeros from these trinomials, or you can complete the square. Just something to be mindful of if you encounter these factor patterns and then go on to solve a polynomial equation from there. Okay, that wraps up our second look at solving polynomial equations by factoring. Next time, we're going to dig into some additional theorems concerning the roots or zeros of polynomials. We'll see you next time.